The field of software analysis is highly diverse. There are many different approaches, each with their own strengths and limitations in aspects such as soundness, completeness, scalability, and applicability. We will learn about a dominant approach to software analysis called constraint-based analysis. Constraint-based analysis follows a declarative paradigm. It is concerned with expressing what the analysis computes rather than how the analysis computes it. In other words, constraint-based analysis is concerned with the specification of the analysis rather than the implementation of the analysis. The analysis specification takes the form of constraints over program facts, while the analysis implementation involves solving these constraints using an off-the-shelf constraint solver. This separation of concerns has many benefits. It simplifies the design and understanding of the analysis. It allows to rapidly prototype analyses, and it enables to leverage continual performance improvements in constraint solvers. We will illustrate these benefits on classical data flow analysis problems using Datalog, a constraint programming language. Designing an efficient program analysis is a challenging task. It involves dealing with both the specification of the analysis, that is, what information the analysis must compute, and the implementation of the analysis, that is, the details of how the analysis should compute the information efficiently. For example, in a null pointer dereference checking analysis, the specification might be no null pointer is dereferenced along any path in the program. As for the implementation, there are several design choices that affect the efficiency of the analysis, such as whether to use a forward versus a backwards traversal of the program, whether to use symbolic versus explicit representations of the program's state, and many others. Even the first choice, whether to traverse the program forward or backward, is a non-trivial decision. A forward traversal involves starting at locations in the program where pointers are set to null and checking if they flow to locations in the program where pointers are dereferenced. A backward traversal involves doing the opposite, that is, starting at locations in the program where pointers are dereferenced and checking if locations where pointers are set to null can reach them. It is easy to see that if a program does not set any pointers to null, then forward traversal is more efficient. On the other hand, if the program does not dereference any pointers, then backward traversal is more efficient. In practice, programs contain a mix of both null pointer assignments and pointer dereferences, making it challenging to determine the most efficient traversal strategy. In constraint-based analysis, the analysis designer defines the specification of the program analysis using what is called a constraint language, and a constraint solver automates the implementation of the analysis. This approach to program analysis has several benefits. Because the analysis specification is separated from the implementation, analysis designers can focus their efforts on specifying what information the analysis must compute, rather than implementing how the analysis should compute that information efficiently. Another benefit of constraint-based analysis is that it yields natural program specifications. Just like types in a type system, constraints are usually defined locally, and solving their conjunction captures global properties about the program. Finally, the modularization of the program analysis task into a specification and an implementation subproblem allows the specification to be agnostic of the implementation. In other words, we can plug and play powerful off-the-shelf constraint solvers, giving us flexibility that would otherwise not be available. To illustrate the difference between the specification and the implementation of a program analysis, let's look at the following quiz. Consider a data flow analysis such as live variables analysis. If this analysis is expressed as a constraint-based analysis, which of the following must the analysis designer still decide upon? The order in which statements should be processed, what the gen and kill sets for each kind of statement are, in what language to implement the chaotic iteration algorithm, whether to take intersection or union at merge points. Check all that apply. Here are the topics we will consider in the remainder of this lesson. Next, you will learn a language called Datalog that can be used to specify constraint-based analyses. Once you have learned the basics of data log, you will see how to use it to specify two kinds of static analyses. First, you will see how to specify an intra-procedural analysis in data log, that is, an analysis that is restricted to a single procedure. In particular, you will see how to specify computing reaching definitions. Then, you will see how to define an inter-procedural analysis in data log, that is, an analysis of a program involving multiple procedures. In particular, you will see how to specify computing points to information. You will also see the extra complexities inherent in defining these types of analysis. Datalog is a declarative logic programming language. It is not a Turing-complete language. It can be viewed as a subset of Prolog or as SQL with recursion. Efficient algorithms exist to evaluate programs in these languages, so there exist efficient algorithms to evaluate Datalog programs. Datalog originated as a query language for deductive databases. It was later applied in many other domains, including software analysis, data mining, networking, security, knowledge representation, and cloud computing, among others. There are many implementations of Datalog. Some of the implementations available include Logic Blocks, BDD BDDB, Iris, and Paddle. You can learn more about Datalog using the resources linked in the instructor notes. We will now present the syntax of Datalog by means of an example program that computes reachability in a directed graph. The problem of graph reachability is to determine all pairs of nodes in a graph that are connected by a path. To express this problem as a program in Datalog, we need to define three things: the form of the input to the Datalog program, the form of the output of the Datalog program, and the rules of inference comprising the Datalog program that compute the output from the input. A Datalog program's inputs and outputs are defined in terms of relations, which are declarative statements that some number of objects are related in some way. A relation is similar to a table in a relational database, and a tuple in a relation is similar to a row in a table. It asserts that the relation holds among some number of objects. For the graph reachability problem, the input is a single binary relation called edge with two arguments n and m. N and m are variables of type node, denoted by capital N, the set of all nodes. This relation encodes the edges in the input graph. For example, for the graph shown here, the edge relation contains tuples 0, 1 and 2, 3, but not tuples 3, 4, 0, 3 or 2, 0. The four tuples 0, 1, 0, 2, 2, 3 and 2, 4 are sufficient to establish the entire structure of the graph. The output of this Datalog program is a single binary relation called path with two arguments n and m, which is true if and only if there is a directed path in the graph from n to m. So, for the graph shown, the path relation should contain tuples 0, 4 and 0, 3, but not tuples 3, 0 or 1, 4. In order for the Datalog program to compute the output relations from the input relations, we must provide rules of inference. These are deductive rules that hold universally. They specify logical if-then statements. The rules of inference that we will define for this problem are, in English, first, there is always a path from each node to itself, which in Datalog syntax takes the form of the rule path x, x, period. Second, if there is a path from node x to y and there is an edge from y to z, then there is a path from x to z. In Datalog syntax, this rule takes the form path x, z, minus path x, y, edge y, z, period. The rules of inference are written in the opposite order that they are typically written in. The hypothesis of an implication is written on the right-hand side, and the conclusion is written on the left-hand side. Relations separated by a comma are ANDed together. The first inference rule, because it has no hypotheses, acts as an axiomatic statement. Finally, a period is used to end each inference rule. Now that you are familiar with the syntax of Datalog programs, I will illustrate the semantics of Datalog programs using the graph reachability example. Conceptually, we start out with the empty path relation and apply each of these two rules, growing the path relation with each application. We stop when the path relation stops growing. A slight variant of this algorithm is depicted here. It starts out by applying the first rule, which involves adding to the path relation each tuple xx for each node x in the graph, capturing the intent of this rule that there exists a path from each node to itself. It then repeatedly applies the second rule, which involves adding to the path relation each tuple xz whenever there exists a node y, such that tuple xy exists in the current path relation and tuple yz exists in the input edge relation. This captures the intent of the second rule, that there exists a path from node x to z if there exists a path from x to some node y, and there exists an edge from that node y to z. This naive algorithm is essentially the chaotic iteration algorithm used for data flow analysis and pointer analysis. In practice, Datalog solvers use much more efficient algorithms for computing the output relations from the input relations and inference rules. The key is that if there are multiple rules, the order in which the rules are applied does not matter. Additionally, the result of the algorithm, like that of chaotic iteration, is the least solution, the smallest path relation that satisfies all the rules. The least solution typically corresponds to what the user wants to compute in many problems. An example of a non-least solution to this problem would be that path xy holds for all nodes x and y. While this relation doesn't violate any rules, it contains many nonsensical paths that would not be desired by a user. Let's look at a run of this Datalog program on an example input. Suppose the input is the following directed graph, encoded by the following edge relation, which contains 4 tuples 0, 1, 0, 2, 2, 3, and 2, 4. The output of this Datalog program on this input is as follows. Applying the first rule, path xx produces all paths of length 0, represented by the following tuples in the path relation 0, 0, 1, 1, 2, 2, 3, 3, and 4, 4. Applying the second rule at this time yields all paths of length 1, represented by the following tuples in the path relation 0, 1, 0, 2, 2, 3, and 2, 4. Applying the second rule again yields all paths of length 2, 0, 3, and 0, 4. Because the path relation doesn't change after applying either of these rules again, the algorithm terminates, yielding the least solution seen here. Let's work on expressing another computation in Datalog in the form of a quiz. Suppose we want to compute the relation SCC, standing for strongly connected component, on a directed graph from the input relations edge and path as we defined them earlier. And suppose we want our Datalog program to output SCC N1, N2 if and only if N2 is reachable from N1 and N1 is reachable from N2. Select each of the inference rules below that will compute the correct output. SCC N1, N2 colon minus edge N1, N2 comma edge N2, N1 period. SCC N1, N2 colon minus path N1, N2 comma path N2, N1 period. SCC N1, N2 colon minus path N1, N3 comma path N3, N2 comma path N2, N4 comma path N4, N1 period. And finally SCC N1, N2 colon minus path N1, N3 comma path N2, N3 period. Now that we have seen the syntax and semantics of Datalog programs, we will consider how to use Datalog to specify an intra-procedural data flow analysis, specifically reaching definitions analysis. The specification of reaching definitions analysis is as follows. Out of n is equal to in of n minus kill of n union gen of n, and in of n equals the union of all out of n prime for each n prime that is a predecessor of n. Here, kill of n is the set of definitions killed at program point n, and gen of n is the set of definitions generated at program point n, and predecessors of n is the set of program points that immediately precede program point n in the input procedures control flow graph. Let us describe the form of the input and output relations as well as the inference rules that would be used to specify reaching definitions analysis in Datalog. The input relations for the analysis should capture all the information from the input procedures control flow graph that is relevant to computing the in and out sets for each program point. While we haven't yet formally defined the inference rules for the analysis, by looking at the specification, we see that in order to compute out of n, we need to know kill of n and gen of n. And in order to compute in of n, we need to know predecessors of n. Therefore, the input relations should give Datalog's constraint solver knowledge of the contents of the kill, gen, and predecessor sets. Moreover, all three of these relations can be computed from the control flow graph of the procedure to be analyzed. Let us define the relation kill with arguments n and d to mean that definition d is in the kill set of program point n. The relation gen with arguments n and d to mean that the definition d is in the gen set of program point n, and the relation next with arguments n and m to mean that program point m is an immediate successor of program point n, or equivalently that program point n is an immediate predecessor of program point m. In these relations, the letter capital N denotes the set of all program points, and the letter capital D denotes the set of all definitions in the given control flow graph. In reaching definitions analysis, we want to compute the in and out sets for each program point. So let us say that in with arguments n and d is the relation that asserts that the definition d is a member of the in set of program point n. That is, definition d may reach the program point just before n. And let us define out with arguments n and d to mean that definition d is a member of the out set of program point n. That is, definition d may reach the program point just after n. Lastly, we specify three rules of inference to compute the in and out sets. These will be based on the formulas for out of n and in of n shown here. The first two rules map to the first rule in the specification, which is out of n equals in of n minus kill of n union gen of n. We use two separate rules to reflect the union of in of n minus kill of n with gen of n, and we use the exclamation mark character to mean that the relation kill nd does not hold. This represents the fact that in of n minus kill of n is the intersection of in of n with the complement of kill of n. Finally, the third rule maps to the second rule in the specification, which is in of n equals the union of all out n prime for predecessors n prime of n. Because this expression is a union, we only need a single inference rule to ensure that all definitions are correctly added to the appropriate in set. For each predecessor n of program point m, each definition d in the outset of that predecessor n will satisfy the hypothesis of this third inference rule. Let's look at an example run of our reaching definitions analysis specified in Datalog. Consider this control flow graph. Program point 1 is the entry point to the procedure. It has a single transition to program point 2, which contains the statement x is assigned 8. Program point 2 has a single transition to program point 3, which is a test of the Boolean expression x not equals 1. If this expression is true, then control flows to program point 4, which contains the definition x is assigned x minus 1, and then transitions to program point 3 again. If the Boolean expression at program point 3 is false, then control flows to program point 5, which is the exit point of the procedure. Recall that the inputs to reaching definitions analysis are the relations kill nd, gen nd, and next nm. Because each definition is associated with a program point, we will label the definitions by the number of the program point they appear at. So the definition x is assigned 8 will be denoted by letting d equal 2 in these relations. And the definition x is assigned x minus 1 will be denoted by letting d equal 4. There are only two tuples in the gen relation of this control flow graph, 2, 2 and 4, 4, as no other program points establish any variable definitions. The next relation can be computed from the directed edges in the control flow graph. Each edge corresponds to a tuple in this relation. This relation thus contains the following tuples: 1, 2, 2, 3, 3, 4, 3, 5, and 4, 3. The kill relation is a bit more difficult to compute. A definition D is in the kill set of a program point n if there is a definition other than D generated at n, and there is a directed path from the point where D is generated to n. Using the graph reachability analysis we described earlier, for example, we can compute that the only such tuple that is applicable for this procedure is 4, 2, capturing the fact that the definition associated with program point 2 is killed at program point 4. Given these input relations and the inference rules described previously, the output relations produced are as follows. The in relation contains the following tuples: 3, 2, 3, 4, 4, 2, 4, 4, 5, 2, and 5, 4. The out relation contains the following tuples: 2, 2, 3, 2, 3, 4, 4, 2, 4, 4, 5, 2, and 5, 4. You can verify the contents of these relations for yourself by using, for example, the chaotic iteration algorithm. To practice specifying a program analysis in Datalog yourself, in the following quiz, define the inference rules needed to compute a live variables analysis. We will wrap up the lesson with a discussion of how to specify an interprocedural analysis in Datalog using a pointer analysis as an example. An interprocedural analysis is an analysis that spans multiple procedures in a program. Let us now consider a flow-insensitive May-alias analysis on programs in the following language. A program in this language consists of functions that have a single argument variable and whose body is a set of simple statements S1 through Sn. For convenience of presentation, we presume that the flow insensitivity approximation has already been applied to the body of the function, enabling us to view it as a set of statements rather than a control flow graph. Each statement is either an object allocation statement, a copy assignment, a return statement, or a call to a function f with actual argument u whose return result is assigned to v. Since we are dealing with a pointer analysis, we are only concerned with pointer typed variables, and we presume that each object allocation site is associated with a unique label. For simplicity, we do not allow field reads or field writes in this language. Let's first look at the intra-procedural aspects of the pointer analysis for our language. For this part of the analysis, We can ignore the function call and return statements, though we'll come back to them when we consider the interprocedural aspects of the analysis. Let's recall the specification of the pointer analysis rules associated with the object allocation and copy assignment statements as depicted in this diagram. Before analyzing an object allocation statement, v is assigned new h if the variable v points to an allocation site labeled h2. Then after analyzing this statement, v may point to both allocation sites h and h2. Likewise, before analyzing a copy assignment statement, v is assigned u if the variable v points to an allocation site labeled h and variable u points to an allocation site labeled h2. Then after analyzing this statement, v may point to both h and h2. Note that in both cases, we accumulate points to facts rather than overwriting them, as this particular pointer analysis performs weak updates rather than strong updates given its flow insensitive nature. The input relations to the pointer analysis correspond to object allocation and copy assignment statements. The first one is new with arguments v and h, meaning that the object allocation statement v is assigned new h appears in the program being analyzed, and the second is assign with arguments v and u, meaning that the copy assignment statement v is assigned u appears in the program. The letter capital V denotes the set of all pointer typed variables in the program, and the letter capital H denotes the set of labels of all object allocation statements in the program. The output relation generated by the pointer analysis is of the form points with arguments v and h, meaning that the variable v may point to an object allocated at the site labeled h. Finally, the inference rules used to compute the points to information are defined to reflect the diagrams depicting the specification of the pointer analysis. The rule for object allocation statements is points vh colon minus new vh period, and the rule for copy assignment statements is points vh colon minus assign vu comma points uh period. Now let us remove the restriction on function call and return statements, which will allow us to conduct interprocedural pointer analysis. Suppose we have the following program to analyze. The program has two statements, an object allocation statement x is assigned new h1 and a function call statement y is assigned f of x. Function f takes a single argument v and has two statements in its body, u is assigned v and return u. To analyze the program, we need to introduce rules for handling function calls and returns. So far, we know how to address the object allocation and copy assignment statements via the input relations new and assign. But how do we handle function calls and returns? The trick is to treat parameter passing and return statements as copy assignments. More concretely, the line y is assigned f of x can be effectively replaced by three lines: v is assigned x, u is assigned v, and y is assigned u. The first line assigns the value of the passed argument x to the variable v. The second line is the body of the function f, which in this case is just the statement u is assigned v. And the third line assigns the value of variable u that would be returned to variable y, receiving the output of the function call. To implement the interprocedural version of the pointer analysis, we need to add input relations capturing function calls, function definitions, and return statements. For this purpose, we use arg with arguments f and v, ret with arguments f and u, and call with arguments y, f, and x, where the letter capital F denotes the set of all functions in the program being analyzed. Arg fv means that the function f is defined with v as its argument variable. Ret of fu means that the function f returns the value of the variable u, and call yfx means that the function f is called with argument variable x and that its output is assigned to the variable y. So, for our example program, we would include the following tuples: tuple fv in the arg relation, tuple fu in the ret relation, and tuple yfx in the call relation. Finally, we add new rules of inference to compute points to information from these relations. The first rule is points vh colon minus call underscore fx, comma, arg fv, comma, points xh period, to reflect the fact that the variable v in the definition of f may point to the same allocation site as the variable x passed into f at the call. The underscore character refers to a wildcard. It doesn't matter what variable is present in that slot, as the output is unaffected by it. And the second new inference rule is points yh colon minus call yf underscore, comma, ret fu, comma, points uh period, to reflect that if variable y receives the output of a call to f and f returns the variable u, then y may point to the same allocation site as u. Suppose you want to compute the relation must not alias for a program in our toy language, where must not alias uv holds if and only if u and v do not alias in any run of the program. Select each of the Datalog programs below that will compute the correct output. The first program consists of a single rule, must not alias uv colon minus points uh1, comma, points vh2, comma, h1 not equals h2, period. The second program consists of two rules, of which the first rule is may alias uv colon minus points comma, points vh period, and the second rule is must not alias uv colon minus not of may alias uv period. The third program also consists of two rules, may alias uv colon minus points u underscore, comma, points v underscore period, and the second rule is must not alias uv colon minus not of may alias uv period. And the fourth program consists of three rules. The first is common uvh colon minus points comma, points vh period. The second is may alias uv colon minus common uv underscore period, and the third is must not alias uv colon minus not of may alias uv period. The rules we have defined so far correspond to what is called a context-insensitive pointer analysis. That is, an analysis that conflates points to information across different calls to the same function. This in turn results in a loss of precision. To achieve a more precise analysis, we introduce context sensitivity. For example, consider this new program. This program has four statements, two object allocation statements. X is assigned new h1 and z is assigned new h2, and two function call statements. Y is assigned f of x and w is assigned f of z. Function f is as before. It takes a single argument v and has two statements in its body. U is assigned v and return u. As before, we could try replacing the function calls with assignment statements. Y is assigned f of x would be replaced by v is assigned x, u is assigned v, and y is assigned u, and w is assigned f of z would be replaced by v is assigned z, u is assigned v, and w is assigned u. Let's build the points to graph that would correspond to the pointer analysis as we have defined it so far. Notice that W may point to H1 and Y may point to H2 in this points to graph. This introduces imprecision into the pointer analysis we have defined so far. W can never point to the object allocated at H1 and Y can never point to the object allocated at H2. One way to add context sensitivity to the analysis is through what is called cloning. Cloning achieves context sensitivity by reproducing the bodies of the procedure in line with distinguished variable names. For example, in this program, instead of replacing y is assigned f of x by v is assigned x, u is assigned v, y is assigned u, and w is assigned f of z by v is assigned z, u is assigned v, w is assigned u, we could introduce different copies of the variables v and u, say vi and ui versus vj and uj for each call to f. In this way, we avoid imprecisely claiming that w may point to h1 or that y may point to h2. Instead, we would have an equivalent program for which pointer analysis would generate a precise points to graph. We can achieve greater precision by allowing cloning to be used for more levels in the call stack. However, the trade-off for precision via cloning is scalability. The deeper we allow function calls to be cloned, the more space and time we need to allow for the resulting analysis. If each function calls just two other functions, the resources needed for a precise analysis becomes exponential in the depth of the stack of nested function calls. In fact, if there are recursive function calls, as in the following program, which is similar to the previous one except that the body of function f recursively calls f, then an infinite cloning depth is needed to differentiate the points to sets of x and y from that of w and z. You can learn more about cloning-based context sensitivity by following the link in the instructor notes. Cloning is not the only way to perform context-sensitive analysis. Another popular approach, called the summary-based approach, uses the incoming program states to differentiate between different calls to the same procedure. Since in general, there may be infinitely many different such concrete states, the analysis designer must apply a suitable abstraction that conflates them enough to enable the analysis to be scalable and terminate, yet make enough distinctions between them to enable the analysis to be precise. Then, the same incoming program states yield the same outgoing program states for a given procedure, and these input-output pairs of program states are called summaries of the procedure. Summary-based analysis is as precise as cloning-based analysis with infinite cloning depth. You can read more about summary-based interprocedural analysis by following the link in the instructor notes. We focused on a particular constraint language, Datalog, in this lesson. However, there are several other constraint languages with different expressiveness and performance characteristics. Here are some of the popular languages, along with the kind of problem that one can express using each of them, and some example solvers for each of those problems. In Datalog, recall that one must specify the analysis in terms of the problem of finding the least solution of deductive inference rules, and example solvers for this problem are logic blocks and BDD-PDDP. SAT is the well-known Boolean satisfiability problem. Using SAT, one must specify the analysis in terms of the problem of determining whether a set of Boolean constraints is satisfiable. Example solvers for this problem are Minisat and Glucose. MaxSat is an optimization extension of the Boolean satisfiability problem. One can specify not only what Boolean constraints must be satisfied, but also an objective function to minimize or maximize. The optimization aspect of MaxSat can be used to express, for instance, various trade-offs in the analysis. Example solvers for this problem are OpenWBO and SAT4J. SMT, the Satisfiability Modulo Theories problem, is an extension of the SAT problem. It allows one to specify not just constraints over Booleans, but also constraints over integers and pointers. Example SMT solvers include Z3 from Microsoft and YASYS. Finally, Max SMT is an optimization extension of the SMT problem, similar to how MaxSat is to the SAT problem. An example Max SMT solver is Z3. In this lesson, we have looked at the benefits of constraint-based analysis and how it separates the specification of an analysis from its implementation. We have also seen how to use a constraint language, particularly Datalog, to set up and solve static analysis problems. The key points to remember are the mapping between the logic of the analysis and the constraints or rules of inference in Datalog, and the mapping between the inputs and outputs of the analysis and the relations by which facts are asserted in Datalog. We have also explored the difficulties and potential solutions that arise in extending pointer analysis to context-insensitive and context-sensitive forms of interprocedural analysis.